Which property of metallic solids is best explained by the delocalization of valence electrons? Okay, so we are now in the world of metallic solids. So we basically have a block, a solid block of a metal. And back to basics, when we learned about the differences of solids, liquids, and gases. And maybe what I'll do is we'll make this a little bit bigger because I'll do the whole shebang. Oh boy, this might be a little bit big, but that's okay. When we learned about solids, right? Solids, liquids, and gases, when we talked about, and this would be a refresher. Well, when we talked about solids, the particles are very close together. So maybe I could fit, oh boy. Please hold as I try to make these very close to each other. Oh boy. You know what? We'll let the corrector do it for me. Beautiful. I'm so glad I thought of it. So we got 1, 2. Oh, jeez. I can't even do this. This is why I was not an artist. Even though I'm okay. I'm okay with art. I'm just drawing circles. Okay, there we go. This is really... Okay, I'm less upset now. Okay, cool. Now, here are my solids. They are tightly packed, right? And usually, when we have a metal, and we'll say a metallic solid, just know that a metallic solid is just a metal. We do not have any nonmetals in here. So this would literally just be a block of iron, Fe, a block of copper, a block of sodium, basically any metal. You can't have any nonmetals in here. And each of these is an atom of that metal, whatever metal we choose. And keep in mind that for all atoms, the interior, aka the nucleus of the atom, has protons and neutrons, but the only charge in the nuclei, the nuclei of the atoms, is the protons. So you have a positive interior, but then that raises the questions of what's going on outside. Well, outside are where the electrons are. And I guess I'll do it in green. Outside the electrons, that's where they're located. So we got electrons around this guy. And this is where it's going to get a little hairy, but whatever. We have electrons around this guy, we have electrons around this guy, and the electrons are always outside of the nucleus, and I'm trying to be as clean as I can be, but you get the gist. So here's where the possibility of those electrons are going to be. But now, as I'm drawing this, you can see that basically I have like a little highway where if I have an electron, and maybe I can draw it. Here's my electron. And if I can just do this, right? Here's my electron. It has a highway. It can go here, but then go in here, and then go in here. And it could basically go anywhere which way it wants because there's basically a highway map between all of the orbitals for the electrons in all of the atoms. That's what it means by delocalization of valence electrons. The valence electrons are where the outside orbits are, right? The outermost shell is the valence electrons, and these electrons can run on the highway system as they please. They are delocalized. Delocalized electrons means that they are not local. D, kind of like, without. It's on the same type of idea with like if you see an A in front of a word, that usually means without. Delocalized, not local. So usually if you have like a local rash, you have just a rash in one place. But if you have a rash all over, that wouldn't be classified as a local rash. So not local means that they can go wherever. And that's exactly what these electrons are doing. They're going down their highway system wherever they want to go, right? Just got to be outside the nucleus. And because of that, you are exposing the positive charge from the negative charges. Keep in mind that the electrons are negative. So when like electrons are moving around when they're going someplace else, they're exposing the positive nucleus. And this idea of exposing direct charges of positives and negative electrons will give us some type of current or some type of electrical charge or conduction of electricity. You need those direct positives and direct negatives, and only the metal properties can basically do that for you. So direct positives and direct negatives allow for conduction of two things: heat and electricity. So that's why when you place a metal spoon when you're, boiling the water for pasta, you put the metal spoon in there, you leave it in the pot for a little bit, and then you touch it, it's going to get really, really, really hot because of that sea of electrons swarming around the whole solid, giving positives and negative charges. So it's because of the delocalization that we have such high electrical conductivity. Metals are usually not going to be brittle. This is a characteristic of nonmetals. High melting point, not necessarily because of the delocalization of valence electrons. That's basically just what metals are. And low density isn't really that specific property for the valence electrons. The only thing for that delocalization or the going down the highway system for the valence electrons is exposing the positives and the negatives so you can conduct heat and you can conduct electricity. So that's why D is the answer. And I hope this helped. Let me know. Let me know in the comments. If you want more questions like this, you can head on over to our website, glazersguide.com. The link will be in the description and at the end of the video in a little bit. But first, gotta listen to the outro music. All right? And then come over to the website. Come hang out. We'll learn tons of stuff, and we're with you guys every step of the way. All right? So I'm proud of you. Keep working hard, and I'll talk to you soon. Bye-bye.
For more practice and for more fun, go to glazersguide.com.
And for more practice and for more fun, come on, go to glazersguide.com.